April 8, 1941, exactly to 35 in the afternoon, and a colossal machine thundered across the tarmac at Nakajima's testing grounds, just beyond Tokyo's sprawling edge. This aircraft was monstrous by any standard, stretching over 100 feet in length, its wings spanning nearly 140 feet from tip to tip. For powerful engines screamed as the behemoth clawed its way into the thick Japanese atmosphere. Engineers from the Imperial Japanese Navy stood frozen at the runway's edge, their expressions betraying years of anticipation and anxiety. 18 grueling months had gone into constructing this bomber. Nearly $1 million American dollars had been spent acquiring the civilian airliner that served as its foundation. They had even staged a fictitious crash to conceal their true intentions from prying eyes. Now, at last, their creation had left the ground. The pilot advanced the throttle levers. The machine gained altitude, but painfully slowly. The engines groaned under the burden. The flight controls responded sluggishly, almost reluctantly. Something was fundamentally wrong. Something had been wrong from the very beginning. The Japanese had acquired American engineering, painstakingly disassembled the most sophisticated airliner ever constructed, and attempted to transform it into a strategic weapon capable of devastating targets across the Pacific theater. What they actually produced was among the most catastrophic heavy bombers ever to take flight. This is the account of how Japan purchased America's discarded airliner and converted it into a monumental failure. It is a narrative of espionage, elaborate deception, engineering arrogance, and the fatal assumption that duplicating someone's creation equals comprehending it. This story begins not with warfare, but with the golden era of American civilian aviation. The year was 1935. Commercial flight was revolutionizing American life. Airlines expanded their networks rapidly. The public grew increasingly comfortable. With air travel, aircraft manufacturers battled intensely to produce the next breakthrough flying machine. Douglas Aircraft Company had recently unveiled the DC-3, destined to become the era's most triumphant commercial plane. Yet before this aircraft even commenced regular operations, airline executives were already envisioning something grander. William Patterson, who led United Airlines, approached Douglas with an extraordinary proposition. He wanted a machine that would render the DC-3 obsolete overnight. Patterson imagined a 4-engine airliner capable of traversing the entire American continent without refueling. It would accommodate 42 travelers during daytime flights or 30 in sleeping compartments for overnight transcontinental journeys. Pressurized cabins would allow passengers to cruise above turbulent weather. Climate control would ensure comfort throughout. This aircraft would represent aviation's absolute frontier. The concept was remarkably bold. No commercial carrier had ever deployed a 4-engine landplane for passenger service. The technologies Patterson described barely existed outside theoretical discussions. Creating such a machine meant solving engineering puzzles never before attempted. The dangers were substantial. The expenses would be astronomical, but the potential payoff was equally magnificent. Whoever successfully built the first 4-engine commercial aircraft would command the industry. For decades, Douglas expressed cautious interest. They recognized this challenge would push their capabilities to absolute limits. They agreed to proceed only after securing commitments from multiple carriers. American Airlines expressed enthusiasm. Eastern Airlines joined the consortium. Pan American Airways and Transcontinental and Western Air, later known as Trans World Airlines, also pledged their support. Each carrier contributed $100,000 toward development. creating a $500,000 foundation for the most ambitious civilian aircraft ever conceived. The engineering obstacles were staggering. Douglas assembled a team featuring their finest designers. Arthur Raymond, who had shepherded the DC-3 program, assumed leadership. The team confronted problems without precedent. How does one construct wings robust enough to support for massive engines while remaining sufficiently lightweight for efficient flight? How does one engineer landing gear capable of supporting an aircraft exceeding 60,000 pounds? How does one route fuel lines, hydraulic systems, and electrical conduits through a fuselage that must simultaneously provide passenger comfort? The challenges multiplied continuously. How does one pressurize a cabin at extreme altitudes without inducing structural stress, leading to metal fatigue? How does one generate adequate auxiliary power for climate control, cabin illumination, and galley operations without overwhelming electrical systems? How does one prepare pilots to operate aircraft twice as heavy and complex as anything previously flown? The team labored for 2 years. They generated 8,100 technical drawings, documenting every aircraft element. They constructed a precise wind tunnel model and executed 866 individual experiments, totaling 1,100 hours. They analyzed airflow characteristics, stability properties, and control responsiveness at velocities and altitudes unprecedented for commercial aircraft. They employed 1,300,000 rivets assembling the prototype. The cumulative engineering investment measured 500,000 man-hours, unprecedented for any civilian aircraft. What materialized was unlike anything previously witnessed. Douglas designated it the DC-4. The aircraft represented innovation from front to rear. It became the first substantial aircraft featuring tricycle landing gear, positioning it level on the ground rather than tilted backward on a tail wheel. This, apparently minor modification, carried profound implications. Passengers no longer climbed uphill when boarding or descended when departing. Cargo handling became simpler. Ground operations grew more predictable. The aircraft appeared modern because it genuinely was. This nose wheel configuration would eventually become industry standard, but in 1938 it represented revolutionary thinking. The wing was enormous, extending over 138 feet between tips. This scale was necessary to generate sufficient lift for the aircraft's mass, while maintaining acceptable takeoff and landing velocities. The design borrowed from the proven DC-3, but was dramatically enlarged. For Pratt and Whitney RT-180 twin Hornet engines mounted on the wings, each generating 1,450 horsepower. The engines were positioned with noticeable toe-out, angled slightly outward rather than pointing directly forward. This unconventional arrangement improved stability by creating favorable yaw characteristics during single-engine emergencies. The tail configuration was perhaps most distinctive. Rather than a conventional single vertical stabilizer, the DC-4 featured 3 vertical fins, one centrally positioned and one at each horizontal stabilizer tip. This unusual design addressed a practical constraint illustrating commercial aviation's operational realities. The aircraft was so massive that a conventional tail would have made it too tall for existing hangars nationwide. Airlines could not afford constructing new facilities at every destination. The triple-tail solution maintained manageable height while providing adequate directional control. An engineering compromise driven by economic necessity. The interior offered luxury unprecedented in commercial aviation. The cabin exceeded any previous airliner in width, permitting more comfortable seating arrangements. Passengers occupied chairs resembling actual furniture. Rather than the utilitarian benches of earlier aircraft, standard configuration accommodated 42 travelers, though Douglas developed sleeper variants with fold-out berths for overnight journeys. Passengers could board in New York, dine, sleep in actual beds, and awaken in Los Angeles. Climate control maintained cabin comfort regardless of external temperatures. Provisions existed for cabin pressurization, though this system remained uninstalled. In the prototype, the cockpit was equally advanced. Power-assisted flight controls reduced the physical exertion required to manage such a large aircraft. Without power assistance, control forces would have been so demanding that pilots could not maintain precision during critical phases. An alternating current electrical system provided dependable power for instruments and systems. Unusual for an era when aircraft typically employed direct current exclusively, auxiliary power units supplied electrical and pneumatic energy on the ground, eliminating dependence on external equipment at remote airfields. On June 7, 1938, the DC for prototype stood ready for its inaugural flight at Clover Field in Santa Monica, California, location of Douglas's primary factory. Carl Cover, Douglas's chief test pilot and among America's most esteemed aviators, occupied the captain's seat. Cover possessed a remarkable career paralleling modern commercial aviation's development. Born in 1893 in Pennsylvania, he learned flying during military service in World War I. He transitioned to test flying afterward, eventually joining Douglas in 1930. He had piloted the maiden flights of the DC-1 in 1933, DC-2 in 1934, and DC-3 in 1935. He had literally steered commercial aviation's evolution with his own hands. Now he was adding another achievement to his legendary record. Cover executed pre-flight procedures methodically, decades of experience having taught him that thorough preparation prevented fatal surprises. The four engines ignited sequentially, each twin Hornet awakening with its characteristic rumble. The aircraft, registered NX-18100 with construction number 1601, proceeded toward the runway. Ground personnel watched with mingled pride and nervousness as 2 years of their efforts faced testing. Cover advanced the throttles, and the massive aircraft accelerated. The DC-4 consumed considerable runway before achieving flight speed. At the appropriate airspeed, Cover drew back the controls, and the aircraft ascended into California's sky. The world's most sophisticated airliner had successfully completed its maiden voyage. The flight lasted approximately 45 minutes without incident. Cover reported the aircraft handled reasonably well, though certain characteristics warranted further examination. Testing continued throughout summer and autumn of 1938. Douglas pilots assessed handling qualities across various speeds and altitudes, evaluated performance during climbs, descents, and maneuvers, and examined system reliability under operational stress. Difficulties emerged as they invariably do with innovative aircraft. Certain systems malfunctioned. Performance figures disappointed expectations. Type certification was postponed while corrections were implemented. On May 5, 1939, the Civil Aeronautics Authority finally granted approval, officially certifying the DC-4 for commercial operations. The prototype transferred to United Airlines for operational evaluation, the decisive moment determining whether the DC-4 represented breakthrough or disappointment. On June 9, 1939, a remarkable event connected the DC-4 to aviation's earliest origins. The aircraft visited Dayton, Ohio, a city profoundly significant to American flight history. Dayton was home to Wilbur and Orville Wright, the brothers who invented powered aviation. Carl Cover brought the DC-4 for demonstrations, and a very special passenger came aboard for a flight above the city. That passenger was Orville Wright himself, then 67 years old. Orville had been just 32 when he and his brother achieved the first powered flights at Kitty Hawk in 1903. That initial flight lasted 12 seconds, covering 120 feet. Now, 36 years later, Orville sat within a 4-engine airliner capable of carrying 42 passengers across the continent. The flight bridged generations of aviation progress. The man who invented the airplane now experienced its most advanced incarnation. Cover later described it as among his career's proudest moments. Despite successful testing and aviation's founding father's presence, United's evaluation revealed severe difficulties threatening the entire program. The DC-4 proved excessively complex for practical airline operations. Its sophisticated systems demanded specialized maintenance unavailable at most airports. Mechanics experienced with DC-3 South struggled with the DC-4's electrical networks, hydraulic circuits, and control mechanisms. Operating expenses far exceeded projections due to the expertise required for continuous operation. Fuel consumption was alarming. Range fell below promises because consumption exceeded design estimates. Performance disappointed in virtually every category, particularly after seating capacity increased from 42 to 52 passengers. For improved economics, this modification pushed gross weight to 65,000 pounds, substantially exceeding original design parameters. The fundamental problem was weight. The DC-4 had grown heavier throughout development as engineers added systems and reinforced structures addressing emerging issues. Every solution seemingly added mass. Engines adequate for projected 50,000-pound aircraft now struggled with 65,000 pounds. One by one, sponsoring airlines delivered their verdict. Pan American and Transcontinental and Western Air had already withdrawn before the first flight, investing instead in Boeing's 307 Stratoliner, a smaller but functional aircraft. Now United, American, and Eastern reached identical conclusions. The DC-4 represented impressive technology unsuitable for commercial service, too expensive operating, too complicated maintaining, too unreliable for scheduled passenger operations. Douglas confronted embarrassing and costly failure. They had invested years and approximately $3 million in an aircraft nobody wanted. The prototype sat at the factory like an albatross. Consortium Airlines paid Douglas $91,000 to $150 each, settling their commitments, a fraction of development costs. Douglas executives debated options. Their answer came in two parts. First, they would redesign a new 4-engine airliner incorporating lessons from the DC-4 failure, simpler, lighter, and more practical. Second, they would attempt selling the original prototype, recovering some investment. That buyer materialized in late 1939 from an unexpected direction. Representatives from Japan's Mitsui Trading Company approached Douglas proposing purchase of the DC-4 prototype for Japan Airlines, known domestically as Dai Nippon Koko. The airline was expanding rapidly as Japan's empire grew, requiring modern aircraft serving routes across Asia and the Pacific. The DC-4, despite its American difficulties, represented technology far surpassing anything available in Japan. Douglas recognized opportunity to minimize losses. The Japanese offered $950,000, substantially offsetting development expenses. The transaction appeared straightforward. A foreign airline purchasing an American commercial aircraft for civilian purposes. American manufacturers regularly sold aircraft internationally. Export restrictions on commercial aircraft were minimal. Douglas saw no reason declining. What Douglas did not know, what the American government did not know, was that Japan Airlines was not the genuine purchaser. The airline served as cover for the Imperial Japanese Navy. The Navy had monitored American aviation developments for years, particularly interested in four-engine aircraft. Japan's aviation industry had achieved remarkable success with single-engine fighters like the Zero and twin-engine bombers like the G5N, but had never attempted four-engine designs. The engineering challenges exceeded Japanese experience. A genuine strategic bomber capable of spanning the Pacific required four engines. Distances involved were too vast for twin-engine aircraft carrying useful weapon loads. American B-17 bombers demonstrated what four-engine aircraft could accomplish. The Imperial Japanese Navy desired that capability themselves. They dreamed of striking Hawaii or even the American mainland. But Japanese engineers lacked knowledge for building such aircraft. The DC-4 offered an almost miraculous solution. Here was the world's most advanced four-engine aircraft, available through normal commercial channels. The Americans had rejected it, but that was America's problem. Japanese engineers believed they could improve the design using Japanese engines and modifications. They would purchase the aircraft, study its construction, learn its secrets, and apply that knowledge building their own bomber. The Imperial Japanese Navy approved the plan, arranging financing through Mitsui Trading Company. Japan Airlines would serve as the transaction's public facade. On September 29, 1939, workers at Douglas's Long Beach factory disassembled the DC-4 prototype and loaded it aboard a freighter bound for Japan, along with the physical aircraft. Douglas provided complete engineering data files accumulated during development, drawings, specifications, test results, performance data, and maintenance documentation. Everything Douglas knew about the DC-4 went into those crates, including the wind tunnel model used for 866 tests. Douglas technicians traveled to Japan assisting with reassembly at Haneda Airport near Tokyo in early 1940. Japanese engineers observed every procedure with intense interest, questioning assembly methods, component purposes, and design rationale. The Americans believed they were providing normal customer support, unaware they were instructing potential adversaries in strategic bomber construction. When reassembly concluded, the DC-4 displayed Japan Airlines' emerald green and silver livery. It was Japan's largest, most advanced aircraft. The airline announced their magnificent new aircraft would soon commence service on prestigious routes. But the DC-4 never transported a single paying passenger for Japan Airlines. Almost immediately after reassembly and initial verification flights, it was quietly transferred to Nakajima Aircraft Company under Navy direction. Nakajima had received a contract developing a long-range heavy bomber designated Experimental Type 13 attack bomber. Specifications demanded minimum range of 3,000 nautical miles, sufficient for reaching targets across the vast Pacific. The DC-4 would serve as their foundation. The Japanese government needed explaining why Japan Airlines' flagship aircraft had suddenly vanished from public observation. They fabricated a cover story worthy of espionage fiction. In mid-1940, Japanese press outlets reported the DC-4 had crashed into Tokyo Bay shortly after departing Haneda. The aircraft was lost, nothing recovered from the water. No further statements would follow. The matter was closed. This story was complete fabrication. The DC-4 had not crashed. It sat in a hangar at Nakajima's facility, being systematically disassembled by engineers documenting every component. The fictitious crash explained the aircraft's disappearance from public view, prevented American intelligence from tracking the prototype, provided cover for the Navy's secret bomber program, and discouraged awkward inquiries about why a brand-new airliner had vanished so conveniently. At Nakajima, engineers worked with intense concentration. They measured every DC-4 dimension. They analyzed structures and systems. They weighed individual components. They traced wiring and hydraulic pathways. They created detailed drawings of Douglas-designed parts. They photographed everything from multiple angles. The aircraft was essentially reverse-engineered to its smallest details. What emerged was the Nakajima G5N, which the Navy designated Experimental Type 13 attack bomber. Nakajima named it Shinzan, meaning deep mountain in Japanese, evoking images of massive strength, imposing presence, and unshakable permanence. The G5N borrowed extensively from the DC-4. The wing was essentially identical, with the same planform, structure, and engine positioning Douglas engineers had developed. The tricycle landing gear was directly copied, providing the same ground handling advantages. Overall size and configuration closely followed the DC-4, but the fuselage was completely redesigned for military purposes. Where the DC-4 had passenger accommodations, the G5N featured a long ventral bomb bay capable of carrying up to 4,000 kilograms of ordnance, roughly 8,800 pounds at maximum capacity, or to aerial torpedoes for anti-shipping attacks. The nose was reshaped with a glazed bombardier's compartment. The cockpit was repositioned higher and further aft. Defensive armament bristled from multiple stations. The distinctive triple tail was replaced with a twin-fin arrangement, more conventional and easier manufacturing with Japanese tooling. The aircraft was designed for crews of 7 to 10 depending on mission configuration. For propulsion, Nakajima selected their own NK-7A Mamoru engines rather than copying the American Pratt and Whitney design. The Mamoru was ambitious, a 14-cylinder, air-cooled radial supposedly producing 1,870 horsepower, significantly exceeding the 1,450 horsepower of the original Pratt and Whitney twin Hornets. The Japanese reasoned more powerful engines would compensate for additional military equipment weight. The first G5N prototype was completed in early 1941. It was impressive sitting on Nakajima's ramp, over 100 feet long with nearly 140 feet wingspan, dwarfing every aircraft Japan had previously built. On April 8, 1941, at 2:35 in the afternoon, the first prototype departed on its maiden flight. Imperial Japanese Navy observers watched anxiously as the massive aircraft climbed away. Japan's first 4-engine land-based bomber was finally airborne. The dream of striking across the Pacific was materializing. Test pilot reports shattered that dream. The G5N was heavy, even heavier than anticipated. The Mamoru engines failed delivering promised power. Theoretical 1,870 horsepower rarely materialized practically. The engines ran roughly, requiring constant adjustment. They overheated during sustained climbs. Reliability was poor, with frequent failures grounding the aircraft. For repairs, flight controls felt sluggish compared to smaller Japanese aircraft. The G5N handled like what it was, an overweight converted airliner straining against design limitations. Performance figures confirmed pilot observations. Maximum speed reached only 261 miles per hour at optimal altitude, far slower than contemporary American or British heavy bombers. The American B-17 cruised faster than the G5N's maximum velocity. Service ceiling barely approached 25,000 feet, limiting ability to fly above enemy fighters and anti-aircraft fire. Climb rate was poor. Most critically, range fell short of requirements. The G5N could fly approximately 2,600 miles, well below the 3,000 nautical mile minimum the Navy had specified. The Navy had requested a bomber capable of striking across the vast Pacific. What they received was an aircraft barely reaching nearest enemy bases, while remaining vulnerable to interception throughout its mission. Dreams of bombing Pearl Harbor or striking the American mainland were clearly impossible. The aircraft simply could not fly that far carrying weapons. Nakajima constructed additional prototypes hoping refinements would solve problems. Engineers modified engine cowlings, adjusted propeller settings, and tweaked fuel systems. Performance improved marginally, but remained far short of requirements. The Mamoru engines continued causing difficulties. They overheated during climbs. They vibrated excessively at certain power settings. They failed inconveniently during test flights. Nakajima engineers were compelled to detune the engines, improving reliability. Running Mamoru engines at reduced power decreased mechanical stress and failure rates, but also reduced already inadequate power output. Performance problems intensified. The G5N was trapped in a vicious cycle. Engines could not produce adequate power for acceptable performance. Pushing engines harder caused failures. Reducing power for reliability made performance even more inadequate. Desperately attempting program salvage, Nakajima built two additional prototypes with different engines. These G5N variants employed Mitsubishi Mk for Kasei engines instead of troublesome Mamoru power plants. The Kasei was proven and reliable, powering the successful G4M Betty bomber with solid reputation for dependability. But the Kasei produced only 1,530 horsepower, significantly less than even derated Mamoru engines. The G5N was already underpowered, with engines theoretically producing 1,870 horsepower, with engines generating only 1,530 horsepower. Performance became truly dismal. The G5N flew even slower, climbed even more poorly, had even less range. More reliable engines made the aircraft safer to fly but incapable of performing its mission. By 1942, the verdict was clear. The G5N Shinzan was a failure. No engine replacement, no modification could overcome fundamental problems. The aircraft was simply too heavy for any available Japanese engine. The Navy had spent years and enormous resources developing a bomber that could not bomb. The Imperial Japanese Army briefly expressed interest. The Army proposed variants designated Ki 68 and Ki 85 using different engines. A full-scale Ki 85 mock-up was actually constructed in 1942 at considerable expense. But the Army observed Navy's struggles with the G5N and wisely decided against repeating their mistakes. The Army cancelled its variants in May 1943 without producing any flying aircraft. The Navy cancelled the bomber program but refused wasting the aircraft entirely. 4 of 6 G5N prototypes were converted into long-range transports. Redesignated G5N and named Shinzan Kai, meaning deep mountain modified. Bomb bays were removed or sealed. Offensive armament was deleted. Defensive armament was reduced. Crew was reduced to 6. The aircraft were assigned to the 1021st Kokutai, a naval air transport unit based at Kisarazu Air Base. For the war's remainder, These four surviving Shinzan transports flew supply missions across the Japanese Empire, carrying cargo and personnel to bases in Hong Kong, Formosa, Tinian, the Philippines, and the Mariana Islands. The mighty bomber that was supposed to terrorize Americans spent the war as a cargo plane. American intelligence eventually detected the G5N's existence through aerial reconnaissance. Following naming conventions developed by Captain Frank McCoy Jr. in mid-1942, they assigned the Allied code name Liz. The Allies assigned this designation expecting the G5N to be a dangerous strategic bomber, unaware Japan had already abandoned that mission years earlier. The threat they prepared for was hollow. The intimidating four-engine bombers they photographed were merely transport planes, making cargo runs. Carl Cover, the test pilot who had flown the DC-4E's maiden flight and taken Orville Wright soaring over Dayton, did not survive the war. When America entered the conflict after Pearl Harbor, Cover returned to military service at General Henry Arnold's request. Cover was promoted to colonel and assigned overseeing B-29 Superfortress production at Bell Aircraft's Georgia factory. On November 27, 1944, Carl Cover died at age 51 in a plane crash during a snowstorm near Dayton, Ohio. He never witnessed victory over Japan Day nor learned what became of the DC-4E he had tested. A street at Long Beach Airport was later named Cover Street honoring him, a modest memorial to a man who contributed enormously to aviation history. None of the 6 G5N aircraft survived the war. The four transport conversions flew until destroyed. Worn out or scrapped, Japanese records from the war's final chaotic months are incomplete, and each aircraft's exact fate remains unknown. By Allied occupation of Japan, no complete G5N remained. The full story of the DC-4E and G5N did not emerge until after Japan's August 1945 surrender. Allied investigators examining Japanese aviation programs discovered documents describing the Shinzan program's origins, the DC-4E purchase, the fake crash cover story, the reverse engineering effort at Nakajima, and the disappointing flight testing results. The irony was profound and instructive. The United States rejected the DC-4 because it was too complex and expensive for civilian use. Japan purchased it hoping to turn American technology against America. Instead, Japan inherited all the DC-4's problems and added new ones. The same fundamental flaws making the DC-4 a commercial failure made the G5N a military disaster. Douglas understood the DC-4's flaws because they had lived through painful development. They knew which design decisions caused problems and why. They possessed institutional memory accumulated over decades. When they designed successor aircraft, they avoided previous mistakes, keeping what worked and discarding what failed. Nakajima possessed none of this context. They could observe what Douglas built, but could not perceive reasoning behind it. They did not know which features represented reluctant compromises. They could not identify which specifications proved impossible meeting. They could only observe the final product, not the painful trial and error creating it. This knowledge gap proved fatal to the G5N program. When Mamoru engines failed performing as expected, Nakajima lacked experience for rapid diagnosis and correction. When the aircraft proved overweight, Nakajima did not understand the decision cascade leading to those weights. When performance disappointed specifications, they could not identify which compromises to accept because they did not comprehend original design intent sufficiently for intelligent modification. Meanwhile, Douglas applied hard lessons from DC for failure, creating something superior. The redesigned DC for emerging in 1942 was essentially a new aircraft retaining only the name and basic four-engine tricycle gear concept. It was simpler, lighter, vastly more practical. The military designated this new aircraft the C-5 for Skymaster, ordering it in enormous quantities. Over 1,200 were manufactured during the war, becoming American military air transport's backbone, flying cargo and passengers across Atlantic and Pacific Oceans. President Franklin Roosevelt used a specially modified C-5-4, nicknamed the Sacred Cow, as personal transport. After the war, C-54s supported the Berlin airlift, delivering supplies to the blockaded city in one of history's greatest humanitarian operations. Many converted to civilian use, serving airlines worldwide for decades. The design that failed as the DC-4E succeeded brilliantly in revised, simplified form. The lesson of the DC-4E and G5N Shinzan extends far beyond aviation history. Technology cannot be stolen complete. The physical artifact represents only part of what makes technology function. The knowledge behind it, the hard-won experience creating it, the institutional wisdom guiding its application. These intangible factors cannot be created and shipped across oceans. Japan spent $950,000 purchasing the DC-4E. They invested years reverse engineering it and developing the G5N. They constructed 6 prototype aircraft. Ultimately, they possessed nothing but for cargo planes and a lesson in technological imitation's limits. Douglas learned from DC-4E's failure, creating one of history's most successful transport aircraft. Japan copied the failure and produced an even greater failure. The G5N Shinzan, the Deep Mountain, was intended to cast shadows across the Pacific Ocean, giving Japan power to strike American territory. Instead, it became a footnote, a cautionary tale about imitation's limits, proof that copying someone else's work is no substitute for understanding your own.